Alright, IB students, today's topic du jour, which is French for the jour, by the way, is the concept of implicit differentiation. So in this video, I hope to address why do we need implicit differentiation, and also understanding how implicit differentiation works with a connection to the chain rule. In addition to that, there's going to be some skills and some concepts, so sit tight and enjoy. Start with, we have this curve, and it turns out this is a standard equation of an ellipse, and it's written as x squared. It also has a y squared in it, so this is different than our usual function. In fact, this is not a function, it's a relation. As I say, if you look at an ellipse, it doesn't qualify as a function by definition. However, we can still understand that there will be a graph. I'll show you the graph of this particular function. There. This is the graph of the function, and it is an ellipse, in fact, but it does have tangent lines all the way around it. If a graph like this has tangent lines around it, then we must be able to do calculus to it as well. So that's why implicit differentiation came about. But a clever student might say, I don't need implicit differentiation. I will solve the equation for y. Express this as two unique functions. I could say, for example, that y is equal to the square root of 4 minus 4/3 x squared, or negative square root of 4 minus 4/3 x squared. The positive will produce the top half of the ellipse, and the negative will produce the bottom half of the ellipse. So why not just do the calculus right here? We can. It would involve using the chain rule with square roots. It's not the worst thing in the world. However, some relations are not so easy to solve. Take, for example, these two. Sorry if you got motion sickness there. The function on the left and the function on the right. Sorry, the relation on the left and the relation on the right. Neither of these is easily solvable for y. It can be done, but it's not necessarily an easy task. And then there are other relations that are not solvable for y, and therefore we need to be able to describe the calculus without just solving for y and differentiating. So, what's an alternative? Well, the first thing we need to do is understand a little bit about derivative as an operator. Just like we can take the square root of both sides or add something to both sides, I can take the derivative of both sides of any equation. So here we have, just so you know, I put in the y value, just the positive half because we're squaring it anyway. Put in the y value in terms of x, and expressing the function, or sorry, the relation, in terms of just x by itself. Now, the issue is it appropriate mathematically to take the derivative of both sides of an equation? So to verify this is true, I'm going to demonstrate some other techniques that we can use with derivative as an operator. Here we have the concept of what looks like the distributive property. It's not the distributive property exactly, but it is a truism that the derivative of a sum is equal to the sum of the derivatives. That's how we've been differentiating polynomials all along anyway. On the right-hand side, the derivative of 1 is 0. Slope of the tangent line, y equals 1. I can take the derivative with respect to x of 1/3 x squared. That's no problem. And here I'm just going to square the square root and then distribute the 1/4, so I can take the derivative of 1 minus x squared over 3, which is negative 2/3 x. I find that 2/3 x plus 0 minus 2/3 x is in fact equal to 0. So what have I shown here? What have I demonstrated? I've demonstrated that it is completely appropriate to take the derivative of both sides of an equation because the equality principle is still retained in spite of the fact that I've taken the derivative. So now we're not just going to go out on faith anymore. We now can use as an operator the derivative, just like taking this, like I said, just like taking the square root of both sides, just like taking the sine of both sides, just like taking the log of both sides. I can now officially take the derivative of both sides of any equation. So practically, how do we do this? Instead of actually solving for y, we can understand implicitly that y is going to be dependent upon whatever value of x I choose. So in other words, y is a function of x within itself. So we're going to treat it like we treat the chain rule. First things first, I'm going to take the derivative of both sides as an operation, And then I can take the derivative of the sum separately. That equals 0. The derivative of 1 is 0. Now, I'll take the derivative of x squared. Oh wait, before I do that, a reminder, the value of y right here depends on x according to this rule right here. So this is what I mean when I say y is within itself a function of x. Take the derivative of x squared over 3 then, that's going to be 2x, 2/3 x to the 1. Now I'm going to take the derivative of y squared over 4, which is 2y over 4. Notice I bring the power down, drop the power by 1. But the chain rule says when we're differentiating with respect to x, we also have to take the derivative of the inside function. So just remember the chain rule like this. The chain rule says if you take the derivative of a function within a composite, take the derivative of the outer function, keeping the original inside, times the derivative of the inside. Hold on, I got ahead of myself here. The example I was going to show is if we take the derivative of the sine of x squared plus 4x, that's equal to the cosine, and then we keep all of the x squared plus 4x inside, and then multiply that by the derivative of x squared plus 4x, which is 2x plus 4. So, just another example of how the chain rule works. We just take the derivative of the outer function, and that is what I did right, hold on a second, that's what I did right here. I took the derivative of the y squared, that's the derivative of the outer function, that's where the sine became the cosine, and then I take the derivative of the inner function, which is the derivative of y in this case, or here it's the derivative of x squared plus 4x. So I hope that makes sense. When we're done, we end up with an equation that has dy dx, that is the rate of change, the instantaneous velocity, as a part of a relation between x and y. Now, all I have to do in this particular problem is find the gradient or slope at the point 1.5, 1, which means I just replace the x with 1.5 or 3/2. I replace the y with 1, and I have dy dx equals 0. So this becomes 1 plus 1/2 dy dx equals 0. Solving for dy dx, we get -2. So that is the slope of the curve, that ellipse that I showed you earlier, when x is 3/2. To verify, I actually found the equation of the tangent line. So I know the slope of the tangent line is -2. I know the coordinates of the point through which the tangent line goes, and so I put that into the point and slope form, and I get this equation. So what I did with the equation was I put both the relation that was given to me at the beginning and my tangent line that I just found, and then I verify that in fact that is the point 1.5, 1, and that the slope of the line that's going through that point is in fact -2. So basically, I just wanted to see that this line is in fact tangent, and according to the graph, it appears to be so. All right, quickly now, before this takes the rest of your lifetime, I just wanted to demonstrate how this works with product rule and some other of the derivative rules that we work with, again, using the derivative as an operator. So here, we're going to take the derivative of both sides of the first equation on the left, and in so doing, I'm going to take the derivative of the sum. And now I have to examine the fact that this is the derivative of a product of the x squared and the y. So I have to use the product rule. I always do this in a different order. It's just because of addition, it doesn't matter. So I just basically whatever's convenient. So I took the derivative of 2x times y, and then I took the x squared times the derivative of y. 1 is the derivative of y. And then I had to use the chain rule, dy dx. Now I have to take the derivative of y with respect to x, which, no surprise, is dy dx. So that is 0. Of course, the derivative of 0 is 0. And now I'm going to find the derivative in terms of x and y. So this equation has two terms that have dy dx in it and one term that doesn't. So I start by removing the term that does not have dy dx as a part of it. Then I recognize that I could factor out a dy dx, treating it like a variable. It is, in fact, a rate of change variable. And, sorry, I got ahead of myself there again. After I factor out the dy dx, I'm left with x squared from here and the 1 from here. And then I'm just going to divide the x squared plus 1 on both sides. So now I have the derivative dy dx in terms of x and y, just as asked for. Now I put, you can't see the input in Wolfram Alpha from this image, but I did put the exact equation as written, and I didn't even ask Wolfram Alpha to do anything with it. I just input that equation, and it gave me all sorts of data, but when I get down here, it says implicit differentiation, and it shows me dy dx, exactly what I have over here. But notice it also has dx dy, depending on which is a function of which. So I have the other form of implicit differentiation with derivative of x in terms of y instead of the other way around, and notice it's just the reciprocal. So anyway, last one. Take the derivative of both sides, which means taking the derivative of the sum, and there's three sums in this case, or the sum of three terms rather. Take the derivative of each. First one, remember, is derivative of, with respect to x of y, so we use the chain rule. That's where I get the 2y, which is the derivative of, 2y of y squared, and then I take the derivative of y with respect to x. That's the chain rule. Here I recognize a product, so I use the product rule again. I take the first times the derivative of y with respect to x, and then I take the derivative of x plus x squared times y. So this is the derivative of this, and this is the y brought down. That's the product rule again. And finally, I take the derivative with respect to x of x cubed. Easy in comparison, it's just 3x squared. No chain rule required because I'm differentiating x in terms of x. Once again, collect like terms, so to speak. I bring out anything that is not multiplied by the rate of change and subtract it over to the other side. I factor out the rate of change term, divide by whatever's left over, and this result happens. You can check that on Wolfram Alpha as well. Thanks for watching. Sorry it went a little long.